Previously, we analyzed bubble sort, selection sort, and insertion sort. We saw how these algorithms were very slow to use in the real world today. In this video, we will look into a much quicker algorithm which is very practical to use, the merge sort algorithm. Welcome to CodeStation. The British had ruled India for almost 100 years. One of the ideologies they had famously used was divide and conquer. In politics and sociology, divide and conquer means breaking up larger centers of power into smaller groups such that the previously larger and powerful groups are weakened. In computer science, we use the divide and conquer algorithms for a similar purpose. Essentially, we break a bigger problem down to a smaller set of problems and solve these smaller problems individually before looking at the whole picture. The merge sort algorithm is a divide and conquer algorithm, which is often implemented in a recursive fashion. Even if we are going to see the recursive implementation of merge sort here, there are other flavors that could be implemented in a non-recursive manner. This is the merge sort algorithm. You can see right away that the merge sort function is recursive. In the merge sort function for the array, notice how we call the merge sort function for the array's left half and the array's right half. This is where the divide part of the algorithm kicks in. We divide the array into left half and right half. Then we call a function to merge the array's left and right half. The fact that we're calling merge after the sort calls suggests that merge function is expecting two sorted arrays. Here, it is expected that the array's left half is sorted and array's right half is sorted too. After the merge operation, we would expect that the whole array is sorted. Thus, we would divide first and then conquer using the merge calls. So, how does the merge function look like? Well, in the merge function, we would first create an array of combined size of array on the left and array on the right. Then, we would start traversing the array elements, comparing them, and copying the elements in sorted order in array 3. In this example, let's say we want to sort in an ascending order. Thus, our comparison of the first element of array 1 and first element of array 2 results that 2 in array 1 is smaller. Thus, we populate array 3 with 2 and move the iterator in array 1 ahead. Then, we compare the next element in array 1 with first element in array 2. Obviously, 5 from array 2 is smaller and thus get copied to array 3. Iterator in array 3 moves on. Now, the comparison is between 8 and 15. 8 gets copied to array 3, then 12 gets copied. There is no more elements in array 1 to compare. The remaining elements of array 2 gets copied to array 3. Thus, array 3 is completely sorted. After that, we would copy array 3 back to array 1 and array 2 such that the original array is now sorted. Finally, we would destroy array 3, which was just some temporary memory space that we used. So, you can see that the sorting comparisons actually happen in the merge call. Now let's go through an example of the entire merge sort algorithm. Let's say we have 7 billiard balls in a random order and we need to sort it in an ascending order. What do we do first? Well, we have to find the midpoint to divide the group into half. The midpoint is around the third point, therefore we will place 3 balls in the left in a separate container and the 4 balls to the right in a separate container. Now, we'd have to do the merge sort on the left half first. Again, we find the midpoint, which is 1, and place 1 ball in the left in one container and 2 balls on the right to the next. Now the leftmost container has only 1 ball and it is already sorted. Thus, we move on to the right unsorted box. What do? Well, we divide the container again. Now at this level, both the containers have 1 ball each. Thus, they're already sorted. Finally, we use the merge function, just like we described earlier, to return a sorted list of balls. Then, at level 2, we have sorted array at the left and the right. These get merged and copied to level 1. At level 1, we have the left array sorted. It is time now to merge sort the right box of balls. We break the problem down, move on to the next level, break the problem down in the left box. At level 3, both boxes have 1 ball each, thus they're sorted. They get merged to level 2 and sorted. Similarly, the right box gets sorted, and finally, these balls get merged to the 4-box container at level 1. Now, level 1 has left and right boxes both sorted. These will get merged and we are brought back to the end of our sorting algorithm. The initially unsorted balls are now sorted. Let's move on to calculating the complexity of this algorithm. For any number of elements, how many times do we conduct recursive calls? This is essentially the number of times that we can divide the number n into halves until n becomes 1. Let's look at some examples. How many times can we divide an array of size 2? 1 time. Array of size 4? 2 times. Array of size 8? Well, 3 times. Half of 8 is 4, half of 4 is 2, and half of 2 is 1. Similarly, we can divide an array of size 16 4 times, array of size 32 5 times, and so on. So, if we look at the numbers carefully, 2 to the power of number of recursion is actually n. So in this case, 2 to the power 1 is actually 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. And 2 to the power 5 is 32. Therefore, the number of recursions are all log base 2 of n. We will call log base 2 of n as log n in this series. Therefore, the number of recursions we do is log n. In our algorithm, we divide the array into singlets, that is, array with single elements, in log n steps. Then, we combine these singlets recursively back to the original array in log n minus 1 steps. So, we have a total of 2 log n minus 1 steps. In each step, we perform n comparison in total. Remember, n is the number of elements in the array. Therefore, the max number of comparisons we do is n times 2 log n minus 1. Asymptotically, this is proportional to n log n. Thus, the complexity of merge sort algorithm is order of n log n. Previously, we looked into quadratic sort algorithms with complexity of order of n squared like bubble sort, selection sort, and insertion sort. Here's how these quadratic algorithms' performance differs from merge sort. For a larger set of data, we see 100% improvement to the number of runs. Thus, this algorithm is much quicker to be used in real world today. However, we have a trade-off. As seen in the merge function earlier, we are required to create an additional temporary memory space of equal size as the array to use this algorithm. If the objects that we need to be sorted are huge in size, and if n is large, an order of n space complexity might not be practical. Also, in case where the device has a small RAM size, it might be unusable. For these cases, the insertion sort might still be better. In the upcoming videos, we will look into other n log n sort algorithms that might be even quicker than merge sort. I hope you liked this video. Please let me know if you have any questions. I'll get back to you as soon as possible. Also, please subscribe to my channel and press the bell icon to get the latest videos. Thank you for watching.